This black ceramic pellet is smaller than the end of your thumb. Used inside a nuclear reactor, one pellet this size can release roughly as much energy as 1 ton of coal. But before it becomes fuel, uranium follows a manufacturing path that sounds almost backward. Rock becomes liquid, liquid becomes powder, powder becomes gas, and that gas is eventually turned back into powder and baked into ceramic. Because natural uranium contains too little of the isotope many conventional reactors need, and the two atoms the factory must separate differ by only 3 neutrons. So how do you build an industry precise enough to notice that difference? And why must uranium become a gas before it can become a solid fuel pellet? The first correction is hidden inside the question itself. Factories do not make uranium. Uranium is a naturally occurring element. Every uranium atom has 92 protons. That proton count is what makes it uranium, and no normal manufacturing process creates the element from ordinary rock. The uranium is already there. What industry makes is usable nuclear fuel. That means recovering uranium from ore, purifying it, changing its chemical form, adjusting the proportion of its isotopes, and shaping it into components that can survive inside a reactor. Not every reactor uses the exact route in this story. Some reactors can use natural uranium. Advanced reactor designs may use different enrichments, fuel forms, or coolants. But this is the classic route used to produce low-enriched uranium dioxide fuel for many commercial light water reactors. And the entire route is built around one rule. Every form of uranium is useful for one job and wrong for the next. Ore can be mined, but it cannot be enriched. Uranium concentrate can be transported, but it is not the ideal form for isotope separation. Uranium hexafluoride can be enriched, but it cannot be loaded into a conventional reactor as fuel. Uranium dioxide powder has the right chemistry, but a reactor cannot operate on loose powder. Each factory solves one incompatibility, then hands a new incompatibility to the factory after it. The uranium remains uranium. What changes is what the next machine needs it to become. The journey begins underground, where uranium is not waiting as a clean block of silvery metal. It is locked inside minerals mixed through rock. Finding uranium is therefore not the same as finding a piece of uranium. Exploration teams study geology, measure radiation, collect chemical samples, drill test holes, and examine cores to work out whether a deposit is large enough, concentrated enough, and accessible enough to recover. Even after a deposit is found, the first product is still mostly rock. In a conventional open pit or underground mine, that rock is broken, removed, and transported to a mill. The mill begins with brute force. Crushers reduce large pieces of ore into smaller fragments. Grinding equipment makes those fragments finer still. That extra surface area matters because the next stage is chemical. The mill does not want to melt the entire rock. It wants to move the uranium out of the solid minerals and into a liquid. The ground ore is mixed with a leaching solution. Acidic systems commonly use sulfuric acid, while some ores are better treated with alkaline chemistry. The exact chemistry depends on the minerals in the deposit, but the goal is the same: convert uranium compounds into a soluble form. For the first time, the uranium leaves the rock, but it does not leave alone. The solution may also carry other elements dissolved from the ore. The mill has separated uranium from solid rock only by placing it inside a new chemical crowd. This is the pattern that follows uranium through the entire fuel cycle. A successful separation is rarely the end of the problem. It is the beginning of a more precise separation. The uranium-bearing solution is processed through systems such as ion exchange or solvent extraction. These processes capture uranium more selectively and separate it from much of the unwanted material. The uranium is then removed from the capture medium, concentrated in a cleaner solution, and precipitated back into a solid. Solid is filtered, dried, and heated into uranium oxide concentrate. Most people know it by a more memorable name: yellow cake. The name suggests a bright yellow powder, but yellow cake is not always yellow. Its color can vary with its composition and processing. What matters is not its appearance. It is what has disappeared. The mine began with a large mass of rock, containing a relatively small amount of uranium. The mill has reduced the useful material into a much smaller volume of concentrated uranium oxide that can be packaged and transported. It has not made reactor fuel. It has made uranium portable, and most of the original material never leaves the site. After the uranium is extracted, the crushed rock remains as mill tailings. Those tailings can contain heavy metals and radioactive decay products, including radium, which can produce radon gas. That is why tailings are not simply pushed into a pile and forgotten. They require controlled storage, water management, monitoring, and long-term containment. The useful product moves forward in drums. Most of the physical mass stays behind, but uranium does not always reach the surface as mined rock. Some deposits can be recovered through wells using a method called in situ recovery. Instead of digging out the ore body, operators inject a controlled solution into uranium-bearing rock underground. The solution moves through the deposit and dissolves uranium into the water. Recovery wells pump that uranium-bearing liquid back to the surface, where ion exchange systems capture the uranium. It is then purified, precipitated, dried, and packaged as concentrate. The rock remains underground. The uranium travels upward in solution. At first, this sounds like mining with the mine removed, but the engineering problem has only changed shape. Conventional mining must move large volumes of rock and manage tailings. In situ recovery must control the movement of fluids underground and protect surrounding groundwater. Not no impact, a different impact, and a different system of control. Both routes eventually arrive at the same unremarkable object, a sealed drum of uranium oxide concentrate. That drum is the first real transformation in the story. The uranium has gone from being a trace component of geology to a material concentrated enough to enter an industrial supply chain. But it still cannot enter the machine that matters most. It cannot yet be enriched. If this is connecting parts of the process you had never seen together, subscribe for more manufacturing deep dives like this, because the next factory takes that solid concentrate and deliberately turns it into one of the strangest industrial gases on Earth. At a conversion facility, uranium concentrate is purified further and chemically transformed into uranium hexafluoride, or UF6. Formula is more than a chemistry label. It is the passport uranium needs to enter enrichment. Natural uranium contains several isotopes. They are all uranium because every one of them has 92 protons, but they contain different numbers of neutrons. About 99. 3% of natural uranium is uranium-238. Only about 0.7% is uranium-235. For many conventional light water reactors, that uranium-235 proportion is raised to roughly 3 to 5%. Sounds like a small adjustment. At the atomic level, it is one of the hardest steps in the entire chain. Uranium-235 and uranium-238 are chemically almost identical. A chemical plant can separate uranium from iron because uranium and iron react differently. It cannot use ordinary chemistry to cleanly separate two isotopes of uranium because their electrons behave almost the same way. The meaningful difference is inside the nucleus. Uranium-238 has 3 more neutrons than uranium-235. It is slightly heavier. That tiny mass difference is the opening enrichment technology needs. But first, the uranium must be placed in a form that can move through a mass separation machine. That is why it becomes UF6. Under controlled conditions, uranium hexafluoride can be handled as a gas. Gas molecules can flow through centrifuges. Solid yellow cake cannot. This detour has nothing to do with what the reactor wants. The reactor does not want uranium gas. The enrichment plant does, and UF6 creates hazards of its own. At ordinary conditions, it can be stored as a solid inside specialized cylinders, then heated for processing. If it contacts moisture, it can form corrosive hydrogen fluoride and uranium compounds. So the plant must control temperature, pressure, containment, and leaks with extreme care. The word uranium makes people think first about radiation. At this stage, the chemical behavior of the material can be the more immediate danger. The UF6 enters an enrichment plant and is fed into gas centrifuges. Inside each centrifuge is a narrow rotor spinning at very high speed. As the gas rotates, molecules containing the heavier uranium-238 isotope tend to move slightly farther outward. Molecules containing the lighter uranium-235 isotope become slightly more concentrated closer to the center. Slightly is the important word. One centrifuge does not take natural uranium and instantly produce reactor fuel. The separation from a single machine is small, so centrifuges are connected into cascades. Gas passes through stage after stage. One stream becomes gradually richer in uranium-235, another becomes gradually poorer. The enriched stream moves forward. The depleted stream moves away as what the industry calls tails. The plant is not plucking individual uranium-235 atoms from a container like someone sorting colored beads. It is repeatedly adjusting the ratio, a little richer here, a little poorer there, again and again until the product meets its required enrichment. And even after that work, the fuel for many conventional reactors is still mostly uranium-238. Raising uranium-235 from about 0.7% to 3, 4, or 5% does not create pure uranium-235. It makes the rarer isotope less rare. Small change is enough to transform how the material behaves in a properly designed reactor. Older enrichment plants used gaseous diffusion. UF6 was forced through porous barriers, and the slightly lighter molecules passed through at a slightly higher rate. The difference was so small that the process required many repeated stages and consumed enormous amounts of electricity. Gas centrifuges exploit the same mass difference far more efficiently. But more efficient does not mean simple. The rotors must spin with extraordinary stability. Vacuum systems, bearings, flow controls, materials, sensors, and cascade arrangements must all work with precision. A difference too small for ordinary chemistry becomes useful only because the machinery repeats it without losing control. The entire enrichment industry is built around 3 neutrons. And then, after all that effort to create a gas, the industry has to get rid of the gas. UF6 is the right form for isotope separation. It is the wrong form for a conventional solid fuel reactor. The enriched material must be converted again, usually into uranium dioxide or UO2. This produces a dark powder. The isotope ratio is now correct for the fuel design. The chemical form is now suitable for ceramic fuel. But the reactor still cannot use it. Powder can scatter, settle, change packing density, and contaminate equipment. A reactor requires fuel with predictable size, density, strength, and thermal behavior. So the next factory stops behaving like a chemical plant and starts behaving like an advanced ceramics factory. The UO2 powder is prepared to meet strict specifications. Its chemistry, particle properties, moisture, and flow behavior must be controlled because those properties affect what happens during pressing and firing. The powder is measured into dyes and compressed under high pressure. Out comes a small cylinder known as a green pellet. It is not green in color. Green means it has been shaped but not yet sintered. The pellet now has the rough form of the finished fuel, but it is still relatively fragile and porous. It looks complete before it actually is. The green pellets enter a furnace. At high temperature and in a controlled atmosphere, the UO2 particles bond and densify. This process is called sintering. The pellet shrinks. Pores close. Its internal structure changes. Loose powder becomes a hard ceramic capable of operating at high temperature. But the furnace solves the strength problem by creating a dimension problem. Because the pellets shrink during sintering, they do not emerge at the exact final diameter required for the fuel rod. They must be ground to size. Then they are inspected. Manufacturers check dimensions, density, chemistry, surface condition, chips, cracks, and other properties defined by the fuel design. This level of attention may seem excessive for something smaller than a fingertip, but the reactor will not use one pellet. It will use millions of them. A tiny inconsistency repeated across an entire core stops being tiny. So the factory is not merely manufacturing pellets. It is manufacturing predictable sameness. Approved pellets are stacked inside long, thin metal tubes called fuel rods. The tube, known as cladding, is commonly made from a zirconium-based alloy in conventional light water reactor fuel. It must hold the pellets in position, help contain radioactive fission products during operation, resist corrosion, and transfer heat from the fuel to the coolant. Those requirements pull in different directions. The cladding must be strong but thin, protective but thermally efficient, stable while exposed to heat, water, pressure, radiation, and years of operation. The pellets are loaded into the tube. Internal components are installed according to the design. The rod is filled and sealed. The welds and the finished rod are inspected. One fuel rod is already a precision product, but it is still not the unit placed into the core. Many rods are arranged into a fuel assembly. Spaper grids hold them in the correct pattern and maintain the gaps needed for coolant flow. Structural components allow the assembly to be lifted, transported, installed, and supported inside the reactor. A typical commercial assembly may contain more than 200 rods, although the exact design varies. A reactor core may contain a few hundred assemblies. The black pellet from the beginning has now disappeared inside a structure several meters tall. One pellet became a stack. The stack became a rod. The rods became an assembly. And the assemblies become a core. Only there does the famous energy comparison begin to mean something. The pellet does not sit on a table releasing the energy of 1 ton of coal. It must be placed inside a reactor that can initiate, sustain, cool, and control nuclear fission. When a uranium-235 nucleus absorbs a neutron, it may split into smaller nuclei. That fission releases energy and additional neutrons. Some of those neutrons can trigger more fissions. A reactor is designed to manage that chain reaction. In many light water reactors, water flows around the fuel rods. It removes heat and also slows neutrons, helping them produce further fissions in the low-enriched fuel. Control rods absorb neutrons and allow the reaction rate to be reduced or increased. The fuel provides the material. The reactor provides the conditions. Heat moves from the ceramic pellets through the cladding and into the water. Heat produces steam directly or transfers energy to a separate water circuit, depending on the reactor design. The steam turns a turbine. The turbine turns a generator. After geology, hydrometallurgy, fluorine chemistry, isotope physics, ceramic processing, and precision metallurgy, the final act is still a rotating machine producing electricity, and now the whole manufacturing chain can be seen for what it really is. Mining solves the concentration problem. Milling solves the rock problem. Conversion solves the chemical form problem. Enrichment solves the isotope ratio problem. Fuel fabrication solves the powder, geometry, and materials problem. Assembly manufacturing solves the positioning and containment problem. The reactor solves the controlled energy problem. No single factory transforms ore directly into a working fuel assembly. The product exists because several specialized industries pass the same element from one incompatible form to another: rock, solution, concentrate, UF6, enriched UF6, UO2 powder, ceramic pellet, fuel rod, fuel assembly. At every stage, the material gains access to one door and loses access to another. Yellow cake can travel, but it cannot be efficiently enriched. UF6 can be enriched, but it cannot serve as a ceramic fuel pellet. UO2 powder has the right chemistry, but it has no controlled geometry. A pellet has controlled geometry, but it needs cladding. A fuel rod contains the pellets, but it needs an assembly to become part of a core. The process is less like one factory line and more like a series of passports. At every border, uranium must show up in the form the next country recognizes. That also explains why there is no single uranium hazard. At the mine, the concerns include rock, dust, ventilation, water, and radiation exposure. At the mill, acids, dissolved metals, tailings, radium, and radon become important. During conversion and enrichment, UF6 containment and corrosive reaction products matter. During fabrication, fine uranium-bearing powder, contamination control, criticality safety, furnace conditions, and exact geometry matter. The name of the element stays the same. The engineering risk changes with its form. Now return to the object from the beginning. A small black ceramic cylinder. No green glow. No exposed silver metal. Nothing about it looks powerful enough to justify mines, chemical plants, centrifuge cascades, furnaces, precision grinders, and years of engineering. But that ordinary appearance is the achievement. Before this pellet existed, its uranium was scattered through geology. It was removed as rock or carried upward in solution. It became part of a liquid chemical mixture, then a precipitate, then concentrate inside a drum, then UF6 inside a cylinder, then gas moving through centrifuges that could detect a difference of 3 neutrons, then enriched material, then dark UO2 powder, then a fragile green pellet, then a dense ceramic ground to an exact diameter, then one object in a stack, inside one rod, inside one assembly, inside one reactor core. The strange part is not only that something this small can release so much energy. The strange part is how many times uranium must become the wrong thing before it can become the right one. Factories do not make uranium. They make uranium usable. Subscribe for more deep dives into how raw materials become precision industrial products, and share this with someone who still imagines uranium going directly from a mine into a reactor. Which transformation surprised you most? Rock into liquid, solid uranium into gas, or powder into ceramic? And if you want to keep following this thread, watch the next video on screen.